Okay, check this out. 219 number 2, they want us to get the direction of the current for each of these different cases. Let's check out this first case. Okay, we got a decreasing upward directed magnetic field B. So through this loop here. So we've got decreasing number of upward directed mag field lines. We're losing them. To make up for the loss, we need B pin to be in the direction of the original magnetic field. To replace, you can think of it as to replace some of those mag fields that are lost. Now remember, here's the deal. Get a changing mag field through a loop. It induces a current in the loop, and that current, by Ampere's law, produces its own magnetic field. And Lenz's law relates the direction of the magnetic field produced by the current that's induced to flow in the wire to the direction of the original magnetic field and how it's changing. And according to Lenz's law, the magnetic field produced by the induced current is going to be in that direction, which tends to keep the number of mag field lines through the loop the same as what it was originally. So what we got going on as a result of the external magnetic field change is a decreasing number of upward directed mag field lines. To make up for that, we need to, the induced current produces a magnetic field in the upward direction to make up for those mag field lines that are disappearing. Okay, now to do that, the question is, what's the direction of the current in the loop got to be? And of course I get out the right hand for that, and I cup the right hand and stick the thumb out. Now B pin is the straight thing here, so I'll align the thumb of my right hand with B pin, and when I do that, I note that the fingers curl around in this direction. I am careful to use the right hand, not the left hand, and as a result of that, I know that the current is in this direction, which I would call counterclockwise as viewed from the top of the page. Alright, let's check this one out. Oh, look, this time we got an increasing B, not a decreasing B. Okay, I'm going to run through the whole argument one more time. Changing magnetic field through a loop induces a current in that loop, according to Faraday's law of induction. So Faraday's law of induction says changing number of magnetic field lines through a loop or coil induces a current in that loop or coil. So we get a current in this loop. Now Ampere's law says, hey, when you get a current in a loop, it's going to make a magnetic field. And so the loop with the current in it produces a magnetic field. Now Lenz's law relates that magnetic field, that end result of the chain of events, to the original magnetic field and how it's changing. Okay, in this case, we've got an increasing number of rightward directed mag field lines occurring. Well, to fight that change, to cancel out some of those, we need a magnetic field in the exact opposite direction to the original mag field. Why in the opposite direction here when it was the same direction here? Well, here it was decreasing when we wanted to help out those fallen soldiers, replace the lost mag field lines. And here it's increasing, and we want to cancel out, in terms of vector addition, some of the newly appearing mag field lines. So this time it's in the exact opposite direction. Okay, then the question is, what must the current direction be in order for the current to have produced a magnetic field line, a magnetic field in the leftward direction from our point of view. This being the front of our loop, and it goes up toward the back across the top, and that's the back of the loop. Now it's coming toward the front, and here's the front of the loop again. And let's see, I'll cup the right hand, stick the thumb out, and I'll stick the thumb. I got the thumb extended so it's pointing to the left, and I see that the fingers are curling around in this direction. So the current in this loop has to be in this direction, as indicated. Over here, it would be downward. You couldn't say up, down, because here is coming like toward the front, and here upward. I really only have to label it one spot, and I've done so up there. Okay, let's move on to this third case. Oh, here's something more interesting in two ways. Instead of just a single loop, we've got a whole coil here, and on top of that, instead of us just telling us what the mag field is doing, we've got a bar magnet which is moving. Okay, the bar magnet's got a magnetic field associated with it. Magnetic field lines, I'm not going to draw a perfect diagram here, but we got mag field lines extending out of the North Pole, looping around, coming in the South Pole. They never cross, so that's a bit of a mistake, just a lack of artistic talent issue. Alright, now here's the deal. Some of these mag field lines are missing the coil, and some pass through it. But the closer the magnet gets, the more of them are going to be sticking through the coil here. So what we've got, our change in the magnetic field through the coil is, we've got an increasing number of leftward directed magnetic field lines. Alright, increasing number. To fight that, B pin's got to be in the exact opposite direction to cancel out some of those newly appearing leftward directed mag field lines. And they're newly appearing leftward directed mag field lines because somebody's moving this magnet toward the coil. Okay, now I just have to use the right-hand rule to figure out the direction of the current that must have been induced in this wire in order to produce this final magnetic field due to the current induced in the wire. Recognize this is the end result. The middleman is the current. So somebody moves the magnet near, we get a change in number of mag field lines through this coil. By Faraday's law of induction, we're going to get a current in this coil. By Ampere's law, the current that's induced to flow in the coil produces its own mag field. And by Lenz's law, the magnetic field produced by the induced current has got to be in that direction, which will tend to fight the change. Okay, the change was increasing number of leftward directed mag field lines. To fight that, B pin's got to be rightward. Okay, now we're to the point where we use the right-hand rule to get the current that would make such a mag field. What's the direction of the induced current? Well, I cup the right hand again, stick the thumb out, and I arrange the hand so it's sticking to the right. And I see that the fingers curl around in this direction. They come downward across the front, upward across the back, or in the back. Tiny little arrow there saying how it's going upward in the back. But as far as the front, it's all down this way. I really only needed one arrow to show it. That would be the current. I'll label that with an I, bright green capital I there. I want to check the question here. I figured you guys had read it before you started this, but I didn't give it a real careful read. In each diagram, which you have to before you submit your final result, indicate by means of an arrow a curved arrow the direction of the current induced to flow in the loop or coil. Okay, I've got it. I was checking to see, in a lot of cases where there's a resistor, the question is which way does it go through the resistor. I'm going to trace this around, trace this current I in the green to see which way it would go through the resistor. Just if you're curious, it comes down in the front, goes around the back, and then down in the front here. So if somebody had asked which way does it go through the resistor, I would have to say in this diagram it goes from left to right. I think I'll draw that up here so it doesn't get mixed in there with the diagram below. Okay. Oh, this is so exciting, huh? Alright, what's happening here? I got a constant mag field, but somebody's yanking the loop out of the region where the mag field is. Okay, if this loop is like all the way over here, of course it's got no mag fields in it. When it was over here, it had more mag field lines through it. So what we got, it's headed, it's going from the situation where it had a whole lot to where it's got some to where it's got none. We got a decreasing number of magnetic field lines through that loop as a result of the motion of the loop. Okay, so this circle dot is supposed to represent an arrow coming at us, and we're losing these arrows coming at us to make up for that. According to Lenz's law, that's what's going to happen. Lenz's law says the magnetic field produced by the induced current is going to be in that direction, which tends to maintain the same number of mag field lines through the loop as there were originally. By the way, it always loses this battle. It tries to maintain the same number of mag field lines, but it loses. But the fact that it tries to tells us the direction. Okay, so we got mag field B pin produced by the induced current coming at us. I'll use the right-hand rule for something curly, something straight. I got a straight thumb, cupped hand, so curly fingers. I'm using the right hand, not the left hand. I got my hand up to the screen with the thumb pointing directly at me, and I note that my fingers are curling around in this direction. So the current is counterclockwise from our viewpoint, but that's all they wanted us to do, was to put an arrow on there, or write none if that was the case. So curved arrow if appropriate. Okay, so we're cool on that. This one, kind of an easy one here. We got decreasing number of mag field lines directed away from us. We're losing mag field lines away from us, so to make up for that loss, B pin has to be directed away from us into the page. If you're copying this or working on paper, into the screen from my point of view. Okay, a little hard the way I'm sitting, but I point my thumb in the direction of the mag field into the screen, and I see that my fingers curl around in this direction. So don't forget that, you know, I find the final result first, and then I find out the most direct cause of that. This is the induced I, or I'll just call it I, the most direct effect of that decreasing B. So changing mag field causes a current, which in turn causes a final end product, namely B pin, which is what Lenz's law relates to the original change that was going on. Okay, what do we got here? Stationary magnet, horizontal loop, moving to the right. I would say, to start with, we had a whole bunch of upward directed mag field lines through that loop, but we're pulling it away from that region where the magnetic field is strong, and so we've got a decreasing number of upward directed mag field lines. So we're losing upward directed mag field lines. To make up for that loss, as we must according to Lenz's law, to be consistent with Lenz's law, B pin's got to be upward. Cup the right hand, stick the thumb out, got the thumb pointing up, and I see that the fingers curl around in this direction. So I will be in this direction, current counterclockwise.